movement diagrams of beams subjected to various loads, and we have seen shear stresses and bending stresses of beams of different cross sections. So what is all our focus in the past two chapters is about bending stress, shear force, and bending force. So these are the four items, two forces and two stresses. That is what we have studied on various types of beams with various types of loads. Is it right? So we have seen various cross sections as well. Now in this class, we'll start unit number 3 of our syllabus. Unit number 3 is torsion and principal stresses. I hope the screen is visible to you. Is it right? Is it visible, guys?
Yes, sir.
Okay, now unit 3 is all about torsion and principal stresses. Let us start with torsion, students. So what is torsion? What is torsion? Anyone? Anyone please respond. What do you understand by this word torsion? We'll be saying no torsion, torque is applied, so the bar is undergoing torsion, the element is undergoing torsion. Torsion is oscillation. No.
Twisting force.
Rotation force.
Twisting force, rotation force, yes. Anything else? All right. Torsion. When do we say that an element is subjected to torsion? See, when an element is subjected to torsion, we say the element is subjected to torsion when we apply some twisting force to that particular element. See, let us consider a circular shaft like this. Okay, and we have twisted it. Okay, we have twisted it, and we have applied some twisting force over this, and we have fixed this side. So we have fixed this side, and I'm trying to twist this bar at the free end. So this is the situation when we say that this element is undergoing torsion. So this kind of situations, if we apply a twisting force at one end of the bar, then we say that the bar is undergoing a torsion. Is it clear? So what is the application of studying this torsion? So why is it necessary to study torsion for beams? Beams or elements, bars, whatever, circular bars, whatever, shafts, whatever it is. So why do we go for torsion? So where do you find this kind of twisting force applications? So in general, where do you experience torsion? Where can we see torsion, students?
Automobile.
Automobile, where an automobile?
Wheel, sir.
Wheels.
Tracks.
Transmission shaft. Transmission shaft. Anything else? See, students, what happens is in an automobile, let us consider, as two of your friends have said, there is an application in automobiles. Let us consider there is an automobile. So you'll get automobile engine at the front end. Let us assume a rear wheel drive, and we have an engine at the front side. So it is a rear wheel drive. Rear wheel drive in the sense these are all the wheels. Let us consider these two are wheels. Okay. So these two are rear wheels. Let us consider a automobile with a rear driven engine. So this is our engine. So this engine will generate us some mechanical energy. Is it right? So by burning the fuel, so from chemical energy, we'll get some mechanical energy here at the end of the engine. Is it right, students? So we burn the fuel, it is a chemical energy. So chemical energy is converted into mechanical energy here, and this mechanical energy has to be transmitted to the wheels. Is it right? Is it right? Do you all know this? Did you get this, students? So there will be a transmission shaft. There will be a transmission shaft which transmits power from an engine to the wheels. So this is wheel shaft. So this is transmission shaft or propeller shaft. We call this as propeller shaft ఆర్ ట్రాన్స్మిషన్ షాఫ్ట్. మీరు ఎప్పుడన్నా పెద్ద పెద్ద లారీలు చూసినప్పుడు కిందికి వంగి చూస్తే ఒక ప్రొపెల్లర్ షాఫ్ట్ ఇంక్లైన్ లైన్లో కనిపిస్తుంది మీకు. సో అది ఏం చేస్తుందంటే ఇంజన్ దగ్గర జనరేట్ అవుతున్న మెకానికల్ ఎనర్జీని, so the mechanical energy that is produced at the engine is being transmitted to the rear wheels here. Is it clear? So this shaft will always be rotating. ఇది ఎప్పుడు తిరుగుతూనే ఉంటుంది. So will this shaft make 100% transmission of power? ఇక్కడ ఎంతైతే మెకానికల్ ఎనర్జీ వస్తుందో అంత మెకానికల్ ఎనర్జీ వితౌట్ ఎనీ లాస్ does this shaft transmit? Does this shaft transmit the entire 100% of energy? Obviously no. There will be no 100% conversion. There will be some losses. That losses may include friction. That losses may include here differential losses, differential friction losses, gear losses, transmission losses. We call them as transmission losses. So there are things that we have to note. And how can we say that this shaft is perfectly suited for this particular RPM? So every engine will run at a rated RPM. So we know that engines run at some rated RPM. And how can we fit a shaft here? To the engine's ability? I hope did you get this? All right. So how do you fix a shaft? So we have to undergo some design criteria. So design criteria involves how much torque that the shaft can withstand, how much load can this withstand, what is the wear properties of this particular shaft that we are using. We'll go through all those things and we'll design a propeller shaft which suits to a particular engine. Is it right, students? So in this process, this torsion has an application. In choosing the design criteria of shafts. So while choosing shafts for different applications, so we have mentioned one application, that is shaft is used in automobiles. There are lots of numerous applications. Like for example, shafts are used in we'll be having turbines, right? We'll be having turbines. So steam turbines and gas turbines will be having both kind of turbines. So steam turbines, in the sense, what happens is there will be turbine blades like this, and this is a turbine. Steam flows into this. Okay, steam strikes the turbine blades so that this turbine blade will rotate. Here, this kinetic energy of the steam, okay, this steam comes with some speed, and this kinetic energy of the steam is converted into the mechanical energy of the turbine. So turbine rotates because of the strike of steam. Alright, steam is striking the turbine blades, so turbine rotates. So mechanical energy is produced here. So what happens is, if you assume this is turbine, I'm just drawing the side view. This is turbine. As turbine rotates, turbine is coupled to a generator. We all know the principle of generator. So in generator, we'll be having rotor and stators. So if this is an AC generator, the rotor will be magnetic field, and stators will be conducting coils. This we have studied in our physics or basic physics. So if turbine rotates, what happens? The generator also rotates. So the turbine is coupled to a generator. Okay, so as generator rotates, because of the stator and rotor there will be EMF induced. There will be EMF induced, and electricity is generated here in generators, and this energy electricity is transferred. So this is how we use shafts at different applications. So here, what I mean to say is there will be shaft between turbine and generator. So this shaft plays a key role in generating electricity. So we have to choose a shaft which can withstand the RPM of this turbine, and which can rotate the rotor of the generator. So that is where we find applications of shaft. This is one application, automobile application. This is turbine application, and we also have shafts in various applications. Like another application is a wind turbine. So there also we have shaft connected to uh, the blades and the generator behind. So if this is a wind turbine, students, so there will be shaft connected to generator in the back end. Okay, so if this is a wind turbine, this is wind turbine, so there will be shaft connected to a generator. So shafts have many applications. We generally talk about shaft. So we generally talk about shaft when it comes to torsion. We do not go for rectangular cross sections or triangular cross sections and all those things. We only speak about circular cross sections. We only speak about circular cross sections. We will come to know why we only use circular cross sections in the next class. Okay, don't worry about this. Why we are using circular cross sections, we'll come to know that in the next class, coming classes. So we generally speak about shafts, so that too circular shafts. So while speaking about torsion, so now let us go to these are all the applications of this torsion and all those things, students. Now let us go to deriving this torsion equation, and let us see the assumptions while deriving this torsion equation, students. So theory of torsion, we say it as theory of torsion, theory of torsion. So let us put some quick assumptions. Okay, assumptions. We'll assume some things for deriving this theory of torsion. So first assumption is material of the shaft is homogeneous, isotropic, isotropic in the sense, students. So there will be no change in properties, no change in properties. Okay, no change in properties. That is what we call it as isotropic, and perfectly elastic. Perfectly elastic. So what we assume is material should be homogeneous, isotropic, and perfectly elastic. So this is assumption number one. And assumption number two is it obeys Hooke's law. Hooke's law obeys Hooke's law. See, students, these assumptions are also very important. So many of the times, the theory question: what are the assumptions of theory of torsion? What are the assumptions in theory of simple bending? This kind of questions arise in your external examinations. And a twisting couple acts in transverse planes only. Twisting couple acts in transverse plane. Acts in transverse planes only. This we'll see why twisting couple acts in transverse plane, and then all radii remain straight. All radii remain straight. Okay, and then parallel planes do not wrap. I'll send you a notes of this in detail. So I'm just writing it in a shortcut. Parallel planes do not wrap. I'll explain you this also. And then last one is cross section at any axial length rotates as a rigid plane. So cross section at any axial length rotates as rigid plane. Okay. So these are all the assumptions, students. Let us quickly see what are these assumptions. I'll show you some figures. Okay. Is it visible, students? I hope you are all seeing this. Is it okay, students? Any doubts so far? Is it okay, guys?
Yes, sir.
Okay. So, students, let us assume a circular shaft. Let us assume a circular shaft fixed at one end. So, this is fixed. Let us assume a circular shaft fixed at one end, and we are applying a twisting moment here. Okay, twisting moment here in this direction, twisting moment over here in this direction. And what are our assumptions, students? The first assumption is material of the shaft is homogeneous. So the entire material of the shaft is homogeneous, isotropic, and is perfectly elastic. Perfectly elastic in the sense it comes back. It comes back if we free the applied torque. మనం అప్లై చేసిన టార్క్ ని మనం వదిలేస్తే if we leave this, it will come back to its original position. That is what I mean to say in the assumption. And second assumption is it obeys Hooke's law. Hooke's law states that Young's modulus or modulus of rigidity G is equals to stress by strain. And then third point is twisting couple acts on the transverse planes only. So if you see here, uh, uh, these are all the transverse planes. So these are all the transverse planes. So twisting couple acts on the transverse planes only. And then transverse planes in the sense మీరు అక్కడ ఏం అజ్యూమ్ చేసుకోవాలంటే అక్కడ అవన్నీ సర్కిల్స్ అంటే ఆల్ దిస్ సిలిండర్ ఆల్ దిస్ సాలిడ్ షాఫ్ట్ ఈస్ ఫార్మ్డ్ బై circles, numerous circles, infinite number of circles. So which I call them as planes, transverse planes. Okay. And then all radii remain straight after torsion. So this radius, students, this radius even after torsion also remains straight. See here, you can observe B and B dash. So these are two radius. One is before twisting and the other one is after twisting. This radius remains straight. There will be no uncertainty in the radius. That is what we mean to say in the assumption. Next is parallel planes normal to the axis do not wrap. Parallel planes normal to the axis do not wrap. See here, let me show you another example. See here. Okay, see this photo, students. So what we have assumed is a circular shaft, that is axis symmetric shaft. So upon the axis it is symmetric. We have assumed a circular shaft. We can also say that it is axis symmetric shaft. So if you assume an axis symmetric shaft, there will be no wrapping or distort after torsion. So the planes normal to the axis do not wrap. Whereas if you assume non-asymmetric axis metric shafts like rectangle, there will be wrapping here. So see here, if you observe here, students, if you observe here, there is wrapping of material. The material is wrapped down. So the material is reduced here. So we are assuming only circular shafts. That is what I mean to say here. So the parallel planes normal to the axis do not wrap or distort after torsion. Even after applying torsion, the wrapping do not happen for axis symmetric shafts. That is for circular shafts. So we are considering circular shaft. That you have to remember. And another assumption is a cross section at any axial length rotates as a rigid plane. So at any axial it will be a rigid plane in the sense. So you have to imagine in such a way that, see here, there are all circular discs in the shaft. So this entire shaft is formed by infinite number of discs like this. Okay, that is what our sixth assumption is. So these are all assumptions, students. So after all assuming all these things, let us try to solve this torsion equation. All of you please listen carefully. So this is very important. Only if you know how to derive this torsion equation, we can say this as theory of pure torsion, theory of pure torsion in circular shafts. In circular shafts, we'll see this, students. So let us consider a circular shaft. I'm just drawing the front view and side view, students. I have already shown you the three-dimensional figure how a circular shaft will be. So let us consider a circular shaft like this, students. So circular shaft which is fixed at this end, and let me take a line which is at the normal. So and I just say it as A. So after applying the twist to this, after applying a twist to this, students, so what happens is this A point moves to A dash. Is it clear? So after applying a twist, A point moves to A dash. Let me draw the side view of this face. This face side view can be seen over here, students. So all of you please see here. Okay, so this is what the side view is, and this distance is R. Let me take this as R, and length of the shaft is L. And radius is R. So after twisting, it moves to A dash. All right. So it moves to A dash. Okay. A to A dash, and this is theta. This is called twisting, angle of twist. Theta is angle of twist. Okay, so this is R. Okay, and here also there will be angle. We just say it as phi. Is it right? So figure shows a circular shaft of length L and diameter D acted upon a torque T. Okay, acted upon a torque T. Let us consider a circular point. Let us consider a point A, which is at a distance of R from the center C. See, this is C, center C, and this is at a distance of R. After applying the torque T, A turns into A dash. A turns into A dash. Is it okay, students? As of now, it is okay, right? Any doubts?
Theta pi same ఉండవా sir?
ಏನನ? Theta
Theta
pi
pi.
same undo. No. See here. Let us go back to the figure again. Okay. Is it okay, students? Did you see the figure? See, what I mean to say is, after twisting, this will be theta. Okay, this will be theta. This is theta, and this is pi. Theta and pi will not be same. Okay, we have applied a twist, and because of the twist, at this plane, at this circular solid plane, it has become from B to B dash. B నుంచి B dash కి చేంజ్ కావడానికి theta angle తీసుకుంది. దీన్ని angle of twist అంటున్నాం. So this is not angle of twist. Okay, this will also form a line. అంటే మీకు ఏమైందంటే longitudinal line ఏమైందంటే longitudinal line has become from AB to AB dash అయింది because of the twist. మీరు ఇక్కడ ట్విస్ట్ చేసిన తర్వాత అబ్జర్వ్ చేస్తే ఆల్ లాంగిట్యూడినల్ లైన్స్ ఆర్ ఇంక్లైన్డ్. ఆల్ లాంగిట్యూడినల్ లైన్స్ ఇంక్లైన్డ్ ఉన్నాయి కదా. ఇంతకుముందు ఎట్లుండినాయి? ఇవి స్ట్రైట్ ఉండినాయి. ఓకే, So these straight lines are twisted. That is what I mean to show here. And this is phi. Okay. We have assumed two angles. So A turns into A dash. Let the angle of twist of A to become A dash. Angle of twist for A to become A dash is theta అని అనుకున్నాం. Okay. So now length of the arc A dash ఏమని రాయొచ్చు బాబు? Length of arc A dash can be given as r theta. రాయొచ్చా? Length of the arc A dash ఇదిగోండి ఇక్కడ చూడండి, అబ్జర్వ్ చేయండి. ఈ ఆర్క్ length can be written as A dash. Okay, from front view also, if you see the front view, from front view, if you see the front view here, we can write the same A dash length, A dash arc length can be written as L pi. Is it right? L pi. So let us equate these two because both are lengths of arc A dash. So equating, we get r theta is equals to L pi. So let us keep this as equation number 1. And now let us write for pi. What is pi? So pi is shear strain at outer surface. Shear strain at outer surface. So shear strain at outer surface antuna. What is shear strain? Shear strain is change in length by original length. So this can be given as distortion at outer surface. Distortion at outer surface is nothing but A dash. Okay. Distortion at outer surface to the original length of the shaft. So pi can be given as A dash by OA. So is it right? If you assume this as O, then O anukunte A dash, sorry. అది సీనే బాబు, ఇక్కడ ఓ ఉంది కదా. Okay, here we have O here. So A dash by OA. So let us just draw this. Deviate and line మాత్రమే మార్క్ చేస్తే ఎట్లుంటో చూద్దాం. ఇది deviate and line. This is O అంటున్నా. This is A and this is what I am calling it as A dash. So what I have written, pi is equals to A dash by OA. అంటే ఏమన్నా రాసిన, ఆపోజిట్ సైడ్ బై adjacent side వేస్తా. Opposite side by adjacent side. So pi, we can take it as, this can be taken as tan pi. Sorry. అసలు పైతో ఏం సంబంధం ఉంది? ఒక్క నిమిషం బాబు, జస్ట్ వెయిట్ ఫర్ ఏ వైల్. ఐ జస్ట్ uh, okay, pi we take pi as shear strain strength, shear strain at outer surface. So shear strain at outer surface can be given as distortion at outer surface by length of the shaft. So pi as per Hooke's law, we have strain, shear strain on actually shear strain pi is equals to shear stress by modulus of rigidity. So this we know, students. ఇది తెలుసు కదమ్మా అందరికి. Stress by strain is equals to modulus of rigidity అని రాస్తాం కదా. So as per Hooke's law, we can write phi is equals to shear stress, we denote it by tau, and modulus of rigidity will denote it by g. So if you substitute this in equation number 1, we get we already have r theta is equals to L pi అని ఉంది కదా. So this implies r theta is equals to L into tau by g. So this can be rewritten for our convenience as tau by r is equals to g theta by L. Tau by r is equals to g theta by L. Okay, or we can also write it as tau is equals to g theta by L into r. Okay, is it clear, students? Any doubts here? So this is half part only, we are just half done. So let me say, any doubts, students? Somebody? If it is okay, we'll move to the another half. Okay, all of you please see and let me know if you have any difficulty. We have just assumed a circular shaft which is fixed at one end. Okay, so just assume a circular shaft or a pen. Take a pen in your hand and fix the pen at one side and twist the pen on the other free side. So that is what I have done here. So after twisting, this is the original position. Actually, OA is the original position. After twisting, this longitudinal axis has changed to OA dash. Similarly, if you see the side view of the same circular shaft, the cross section, if you see the cross section, this A has become to A dash, and I am assuming this angle between A and A dash as theta, which we call it as angle of twist. So I have just written the length of arc A dash in both side views and front views. If you see it in the side view, we can say the length of arc as r theta, and if you see it from the front view, we can say A dash as L pi. So what is pi here is pi enduku nenu strain antunante, strain is change in length by original length. Ikkada chudandi, if you observe here, OA is the initial one. So after applying the twisting movement, it has become as OA1. Is it right? OA dash, it has formed to OA dash. So there is a change in length because of the application of the torsion. So that strain is nothing but distortion at the outer surface by length of the shaft. We'll know, we just say pi as strain. So strain by Hooke's law, as we are saying that in the assumptions, this follows Hooke's law, obeys Hooke's law. Hooke's law states that strain is equals to stress by modulus of rigidity. So pi is equals to stress by modulus of rigidity. So pi is equals to tau by g and rasuna. Modulus of rigidity is represented as g, and shear stress is denoted by tau. So pi is equals to tau by g అని దాన్ని సబ్స్టిట్యూట్ చేస్తాం. And substitute చేస్తే I have got these two equations. Is it okay, students? So here what is tau? What is tau, students? What is tau, guys?
Shear stress, sir.
Okay. What is r?
Radius of shaft, sir.
Okay. G is modulus of rigidity, theta is angle of twist, L is length of the shaft. Okay. So we are half done. Now let us consider a small strip in the circular shaft. So we have seen this circle, right? So we have this circular shaft, and let us consider a small circular uh, let us consider a small circular strip along the same surface. ఇదే క్రాస్ సెక్షన్ లో ఇంకొక స్మాల్ సర్క్యులర్ స్ట్రిప్ అజ్యూమ్ చేసుకున్నాం. ఓకే, సో చిన్న సర్క్యులర్ స్ట్రిప్ ని అజ్యూమ్ చేసుకుంటున్నాను. అండ్ దిస్ సర్క్యులర్ స్ట్రిప్ ఈజ్ అట్ ఏ డిస్టెన్స్ ఆఫ్ స్మాలర్. ఇక్కడ కూడా కన్ఫ్యూజ్ కావద్దు, ఇది స్మాలర్ డిస్టెన్స్ లో ఉందని అనుకుంటున్నాను. అండ్ డయామీటర్ ఆఫ్ దిస్ అంటే థిక్నెస్ ఈజ్ dr. Okay, thickness of this small strip is dr. So I'll just write it as, my god, okay, I'll just write it as consider a ring of radius r and thickness dr on the cross section. Okay, on the cross section like this, as I have shown in the figure. So this is our cross section, and in the cross section I have just considered a ring. Let us write what is force acting on this. 1 second, students. My mouse has gone down. All right. Okay. So because of the twisting movement that we have applied, twisting torque that we have applied, there will be some force acting on this ring. And let me write for that force. Force acting on the ring. I just assume it as df. ఇది dr అనుకున్నా కాబట్టి ఇది కూడా df అనుకున్నా. వెరీ స్మాల్ పోర్షన్ అజ్యూమ్ చేసుకుంటాం కాబట్టి d టర్మ్స్ లో అజ్యూమ్ చేసుకుంటాం. సో df క్యాన్ బి గివెన్ యాజ్ force అంటే force can be given as stress multiplied by area, right? So area, let us take this area as dA. Stress is tau. So stress is equals to force per area అని రాస్తాం కదా, అప్పుడు force is equals to stress multiplied by area అని రాస్తాం. That's it. Now let us write the movement for this. Movement అయితే ఏముంటుంది రాద్దాం. Movement acting on ring dm. So dm is equals to movement అంటే force into distance. df అనేది force, distance is r from the center. So df into r. Now we know that tau is equals to, tau we have already derived, students. Tau is equals to g theta by l into r అని మనం డిరైవ్ చేసుకున్నాం కదా, అది సబ్స్టిట్యూట్ చేద్దాం. So if you substitute that, what do we get, students? dm is equals to df already మనం రాస్తాం కదా tau అని, tau into dA into r కదా. So this becomes tau is g theta by l into r square అవుతుంది into dA. Okay, this is for dm. dm is moment for small strip. So dm is moment of small strip. So for entire cross section, m. So m can be taken as, so if you integrate this dm, we'll get m. So m is equals to integral over dm, that is equals to integral over g theta by L into r square dA. So here z theta by L is a constant thing, so we can take that out. So m is equals to g theta by L integral over r square dA. What is integral over r square dA, students? Integral over r square dA is polar moment of inertia. This is also we have studied. I'll just brief you. Is the polar moment of inertia. Is the polar moment of inertia of the circular cross section. Of the circular cross section about polar axis. So you have to note this about polar axis. So you might have studied this, students. I'll just going back to your first year engineering mechanics. So you might have studied this. Izz is equals to Ixx plus Iyy. So Izz is nothing but polar moment of inertia. So if you see Ixx, so integral over x square dA is nothing but Iyy. Integral over y square dA is nothing but Ixx. So we have seen this, students. I don't know how many of you remember this. Integral over r square dA is equals to Izz. So we have seen all these things in our first year, and also Ixx is nothing but here Izz is equals to Ixx is pi d power 4 by 64 for circular cross sections plus pi d power 4 by 64. Iyy is also pi d power 4 by 64. Yy and xx, see if this is a circular cross section and this is x and this is y, and z will be like this. Okay, so z will be acting like this. If this is x and this is y and this is z. So for x and y it is pi d power 4 by 64. For z it is pi d power 4 by 32. This becomes pi d power 4 by 32. Did you remember this, students? So let us come back to our equation. Our equation is m is equals to g theta by L into j. J, what is j? J is polar moment of inertia, that is integral over r square dA. Okay, so this is one derivation that we have derived. M can be replaced by applied torque. Applied torque. See, students, M is a resistive movement. So M is a resistive movement because of the applied torque. So moment here can be replaced by torque. So I'm just replacing M to T. So this implies T is equals to g theta by L into J. So this equation can be rewritten as P by J is equal to g theta by L is equal to, we also have this tau by R. See, students, this is very important relation. Very important relation. T by J is equals to tau by R is equal to g theta by L. T is applied torque. So if you take a circular shaft like this, T is applied torque. So the torque that we have applied is T. J is polar moment of inertia of the circular shaft. So polar moment of inertia for circular shaft will be pi d power 4 by 32. And G is modulus of rigidity or modulus of elasticity, we call it as. And theta is the angle of twist. So because of the applied torque, how much is the angle of twist? And L is length of the shaft. Tau is shear stress developed because of the application of the torsion. Because of the application of the torsion, there will be shear stress developed, and R is the radius. R is the radius of the circular shaft. Is it clear, guys? So there will be problems based on this relation. T by J is equal to G theta by L is equal to tau by R. They'll give some of the unknowns here, and they'll ask us to find out another ones. See, T, J, G, theta, L may be given, and we will be asked to find out tau and R like that. There will be problems like this. Okay. I hope it is clear for you, and please let me know if you have any doubts, students. So this is very simple derivation, students. The only thing is you have to draw the figure carefully. So OA and OA dash, I have written A dash in both the ways. So in front views and side views, I have written for A dash. In front view, it has become as L pi. In side view, it has become R theta. So I have equated both of them. R theta is equals to L pi. I equation చేసేస్తున్నాను. సో ఇక్కడ పైన ఏం చేస్తున్నా అంటే పై ఈజ్ నథింగ్ బట్ షియర్ స్ట్రెయిన్ అంటున్నా బికాస్ ఆఫ్ ద చేంజ్ ఇన్ లెంత్. సో బికాస్ ఆఫ్ ద అప్లైడ్ టార్క్ దెర్ ఈస్ అ చేంజ్ ఇన్ లెంత్. సో పై ఐ హ్యావ్ ట్రీటెడ్ ఇట్ యాజ్ షియర్ స్ట్రెయిన్. So shear strain, we all know that stress by modulus of rigidity. I have taken it tau by g. So pi and tau by g substitute చేస్తే I got the first relation. Tau by r is equals to g theta by L. This is my first relation. After getting this relation, I am assuming a small strip. I am assuming a small strip with radius r, at some distance, okay, with the thickness dr. After that, I have just written equations for force. All of you see here, I have written nothing confusing. So just written equation for force. Force is nothing but stress into area, and then movement. Movement is force multiplied by distance. This we know, and then substituted. So dm, I have got dm for small strip. So I need for entire cross section. So for getting for entire cross section, I have just integrated this. So if I integrate it, z theta by L is constant, so I have taken it out. Integral over r square dA has remained for me. So integral over r square dA can be taken as j, which is polar moment of inertia. So that we have studied in our first year. అది కూడా మార్క్ చేసిన ఇక్కడ పోలార్ మూమెంట్ ఆఫ్ ఇనర్షియా గురించి చెప్పిన. So m is equal to g theta by L into j. So based on the both relations that we have derived, we are writing this relation T by J is equals to tau by R is equal to G theta by L, which is very important, and you have to remember at any cost. Okay. Any doubts, students? Please let me know if you have. Kiran, is it okay?
Yes, sir.
Okay, guys. If you have no doubts, you can leave and join for the next class. If you have no doubts, you can join for the next class. Otherwise, please stay back and ask me the doubt.